All of you, welcome to the session. Today we are going to talk about adiabatic demagnetization. So this is one of the techniques to get the low temperatures. Okay. Let us see here what happened in this method, in this technique. So when a paramagnetic substance is magnetized, the molecules, the molecular magnets that are lying in random manner are aligned in the direction of magnetic field. So certain amount of external work is done in this process and is added to the internal energy of the substance. You know that how can we do external work? By applying the magnetic field. Okay. See there one more point. If the magnetization takes place in adiabatic process, the temperature of the substance increases. Right? If the magnetization takes place in the adiabatic process, the temperature of the substance increases. If the magnetization takes place in isothermal process, the temperature of the substance remains same. Okay. When magnetic substance is already magnetized, when a paramagnetic substance is already magnetized, it is suddenly demagnetized, the energy required for demagnetization is taken from paramagnetic substance itself. This results in fall in temperature of the substance. If the substance is already at a sufficient low temperature, the fall in temperature is considerable. This process is called adiabatic demagnetization. So here you have to remember that the final temperature depends on the nature of paramagnetic substance and intensity of magnetic field. Okay, so let us see the technique of adiabatic demagnetization and how can we get low temperatures in this experiment. So now, just now have seen adiabatic demagnetization. In this adiabatic demagnetization, let us see experimentally how can we get very low temperatures with the help of this diagram. Okay, so let us see here. I am taking chamber A. See, this center portion is called chamber A. In this chamber A, we are taking paramagnetic substance. See there, where P is a paramagnetic substance, so that is nothing but what type of paramagnetic substance is this? What? Gadolinium sulfate. I am taking their gadolinium sulfate substance which is hanging in the chamber A. Okay, now, so this chamber A wounded by coil. See there, where M is a coil, wounded by a coil. So the coil is used to measure the temperature of the substance. Okay, this coil is used to measure the temperature of the substance. Right. Now this chamber A is surrounded by another liquid, that is what? A liquid helium. So chamber A is surrounded by liquid. That liquid is called liquid helium, which is at 1 degree Kelvin temperature. That liquid helium is at 1 degree Kelvin temperature, that is taken in the Dewar flask B, where the liquid helium taken in the Dewar flask B. Okay. Now again, this Dewar flask B, again which is surrounded by another liquid, that is what we can say liquid hydrogen. I am taking their hydrogen liquid in the Dewar flask C. Okay. So in the Dewar flask C, I am taking hydrogen liquid. In the Dewar flask B, I am taking the helium liquid which is at 1 degree Kelvin. Okay. Now, so either sides of this experiment, I am taking the strong magnetic field. There is the strong magnetic fields. Okay, so between these two poles, right? All right. Now here chamber A also connected to the vacuum pump, which is also connected to the vacuum pump. So this is all about the parts of experiment. Let us see how can we get low temperatures. Okay. Now initially what we can do here. So initially what I am taking a gadolinium sulfate, which is acts as a paramagnetic substance, which is hanging in the chamber A. Now the chamber A is filled with the helium gas. See there, initially chamber A is filled with the helium gas. As a result, what happened? There exists a thermal contact between the paramagnetic substance and liquid helium. See there, if we take helium gas, when the chamber A is filled with helium gas, immediately there exists a thermal contact between the substance and the liquid helium. As a result, what happened? The temperature of the paramagnetic substance become 1 degree Kelvin. Okay, so the temperature of the paramagnetic substance, otherwise the temperature of the gas, so here I am taking helium gas, is equal to 1 degree Kelvin. Okay, so it is filled with the helium gas. Okay, now what happened? After a certain time, the substance, here paramagnetic substance, attain the temperature 1 degree Kelvin, which is equal to the temperature of liquid helium. Now what we have to do, let us apply strong magnetic field. That means what I am taking, I am trying to magnetize the paramagnetic substance. I am trying to magnetize the paramagnetic substance by doing external work, by applying magnetic field, strong magnetic field. So I am magnetizing the paramagnetic substance. You know that when we apply magnetic field to the paramagnetic substance, where the paramagnetic substance contain molecules which are moving randomly. So as soon as I applied magnetic field, immediately they aligned in the magnetic field direction. Okay, they aligned in the magnetic field direction. Right. So in this process, what happened? The temperature of the magnetic substance, the temperature of the paramagnetic substance is slightly increased. The temperature, as soon as I apply the magnetic field, immediately magnetization takes place within the substance. As a result, the temperature of the paramagnetic substance is slightly increased. But what happened? You know that there exists helium gas within the chamber. Now that generated where the temperature increased, so now the heat energy is transferred to the liquid helium through a helium gas. As a result, now again the temperature of the paramagnetic substance remains unchanged. That means the temperature of this paramagnetic substance is 1 degree Kelvin. Now what we have to do here? Now we have to send helium gas, which is already there in the chamber, to the outwards direction. I am releasing this gas to the surroundings, to the outward direction. As a result, what happened? So there is a vacuum is there between the paramagnetic substance and the liquid helium. That means there is no thermal contact. There is no thermal contact between paramagnetic substance and the liquid helium. So as a result, what happened? There is no energy transfer takes place between the paramagnetic substance and the liquid helium. Okay, now what I am doing, I am switched off the magnetic field. Then what happened? Demagnetization takes place within the substance. Right? As soon as I switched off the magnetic field, demagnetization takes place within the paramagnetic substance. To make it demagnetize, the substance required some energy. Right? The substance required some energy to do some work. So what happened? There is no contact to the surroundings. As a result, what happened? That the molecules within the substance receives energy from the substance itself. As a result, what happened? The temperature of the substance again decreased. Okay, so when I switched off the magnetic field, demagnetization takes place within the system. The demagnetization takes place in the adiabatic process. You know that there is no contact between the surroundings and the substance. In this adiabatic process, system molecules to do some work, it receives energy from the substance itself. As a result, then the temperature of the paramagnetic substance is decreased. That temperature of the paramagnetic substance is measured with the help of susceptible measurement, that with the help of magnetic, here coils are there, with the help of these coils we can measure the temperature of the substance. In this way we can attain low temperatures by using this adiabatic demagnetization equipment or experiment. Okay, now after this we have to see theoretical explanation. See that we can see, we are going to see theoretical explanation. So what are the relations are there, how this temperature change is depends on the another things, energy and magnetic field. Let us see theoretically about that. Okay, now let us see theory of adiabatic demagnetization. Okay, now when the paramagnetic substance is magnetized, the molecules in the substance align in the direction of magnetic field. Now already I have seen where the paramagnetic substance is placed within the magnetic field density B. Where the paramagnetic substance is placed within the magnetic field density B, so that is represented by capital B, magnetic field density. Now intensity of magnetization is represented by I. Now the change in intensity of magnetization, can be taken as dI. This is B is nothing but magnetic field density, where dI is change in intensity of magnetization, and the resultant work done during the magnetization process. The work done during the magnetization process by externally can be equal to W equal to B dI. The work done by the magnetic field. On the substance can be W is equal to B dI. Okay. So now what we are doing after this? Now demagnetizing. So during the demagnetizing, what happened? To make it demagnetize the substance itself can utilize the energy, otherwise itself it draws the energy from the substance itself. Okay, so because there is no external energy transferring from the surroundings to the substance. Okay, so during the demagnetization process, the substance itself, it utilizes its internal energy, that is also equal to W equal to minus B dI. So this is what the work done. The work done by the substance during the demagnetization process. Demagnetization process. So in the magnetization process, the work done on the substance by the field is how much? W is equal to B dI. Okay, but in the demagnetization process, the work done on the subjects itself can be W is equal to minus B dI. Okay, you have to remember. Then the resultant work done. Resultant work done can be dW equal to what is that? PdV minus BdI. PdV minus BdI. Okay. So this is what equation number 1 and this is what equation number 2. And also we know that here, so here according to thermodynamic first law, we know that TQ equal to du plus dW. Okay, we know very well. Substitute equation 2 in this equation, and also, so then what we get, the dQ equal to du plus PdV minus BdI. Okay, what is dq? We know that according to thermodynamics second law, dq equal to TdS. Write down TdS equal to du plus PdV minus Bi. Now, let us assume demagnetization process takes place at constant pressure. Let us assume that demagnetization takes place at constant pressure. At constant pressure. So, at constant pressure, there small change in volume at constant pressure, change in volume is negligible. Therefore dv equal to 0. Substitute dv equal to 0 in this equation, then what we get there, tds equal to du minus b di. TDS equal to du minus PDS. Actually, what is TDS? Actually, this, let us assume this is what equation number 3, and actually we know that TDS equal to du plus PdV, right? Du plus PdV, we know this one equation. Now, according to Maxwell's thermodynamic equations, the equation related to entropy and pressure, the equation related to entropy and pressure can be written as, here dou by dou S equal to dou by dou P. Okay, here it is V, here we can write T. Okay, T equal dot like that. So here it is constant pressure and here it is constant entropy. This is Maxwell's third law, Maxwell thermodynamic equation 3, the relation between entropy and pressure. Okay, now what we have to do, we have to replace here, replace V by I and replace P by minus B. Okay, so what I am doing, I am replacing P equal to P equal to minus B, and where V equal to I am replacing there. So what I get here, if we replace here, so what I get here, dou I by dou S, so that equal to minus, so here what we get there, dou T by, instead of P what we have to write, dou B. Now here it is B and here it is S, we have to write there. Okay, alright, next. From this equation I am writing there dou T by dou B constant entropy equal to minus, here I am writing this one as dou I by dou T and dou S by dou T. Okay, so at a constant magnetic field, I am doing like that. Now, so assume this is what equation number 5. Okay, next let us see what I am doing here. So from that equation, let us take denominator part. So dou S by dou T B. So let us here multiply and divide with T, then we will get 1 by T and T dou S by dou T constant B, and we know that TdS equal to dQ. Similarly dou Q, then we will get 1 by T. Here this can be written as dou Q by dou T at B, where dou Q by dou T is nothing but specific heat capacity that is represented by C at constant magnetic field density. So then what happened, 1 by T, so this can be written as Cb. That means finally we'll get there equal to Cb by T. Okay, Cb by T. So substitute now this Cb by T in this equation. Okay, in that equation, let us see what we get there. In the equation 5, let us assume this is what, 6. Substitute 6 in 5. What we get there if you substitute here, then we'll get there dou T by dou B S equal to dou T by dou B S equal to, so which remains same, minus dou I by dou T at B by, and this value should be what there, Cv by T. So finally what we get there here, Cv by T, and finally we will get there dou T equal to minus T by Cv into here it is what there, dou I by dou t at constant b into dou v. Assume this is what equation number 7. Equation number 7. Okay. So you have to remember that equation. Now susceptibility can be written as, now the susceptibility can be written as psi is equal, sorry, I by B. We know that I means intensity of magnetization, where B is magnetic field density, psi equal to I by B. So according to Curie's law, assume this is what equation number 8. So according to Curie's law, psi is equal to Cc by capital T. What is Cc there? Curie's constant, where Cc represents Curie's constant, where T is temperature. So according to Curie's law, susceptibility can be Cc by T, where the susceptibility cannot depend on intensity and magnetic field. It depends only on the temperature. Based on temperature, susceptibility will be varied. So let us make it equal, equation 8 and 9. And then what we get there, I by B equal to Cc by T. Okay, I by B equal to Cc by T. So now differentiate this equation with respect to T. So differentiate that equation with respect to T. Let's see what we get there. Assume 10, differentiate 10 with respect to T. Then what we get there with respect to T. What we get there? So here we get there 1 by B into dou I by dou T, that equal to minus Cc by T square, minus Cc by T square will get there, minus Cc by T square. Now assume this is what equation number 11. Okay, so substitute equation 11 in equation 7. Okay. So substitute equation 7. So substitute 11 in 7. See what we get there, in place of dou I by dou T. In place of dou I by dou T, I am substituting this equation. Then what we get there, dou T equal to minus T by CB, dou I by dou T equal to minus Cc by T square into B, and here it is what there, dou B is there. Right, this one cancel, where minus cancel. So finally what we attain here, now the equation is 1 by T into Cc by Cb into B into dou B. This is the change in temperature of the paramagnetic substance. Okay, that is what the equation, changing temperature of paramagnetic substance. Now what I am doing here, so again I am taking this equation as T into dou T, that equal to Cc by Cb B into dou B. Okay, now the temperature is varying, where the temperature is varying between the temperatures Tf and Ti, and where the magnetic field, if the temperature increases, where the magnetic field is decreasing. Then as a result, what happened here, I am taking, here B goes to 0, so here I am taking integral T dt, the values can be taken as Ta to Tf, so that equal to Cc by Cb constant, and here I am writing B to 0, putting minus. Instead of taking 0 to B, I am taking B to 0, that is why I am putting the minus, and B dV. Okay, now integrating that equation, let us see what we get there. See, this can be Tf square minus Ti square. You know that integration of T can be what? T square by 2, then we'll get to 2, that equal to, where minus Cc by Cb. Here also we'll get there B square by 2, and the limits go to B to 0. Okay, so 2 get cancelled, then finally we'll get there Tf square minus Ti square, that equal to minus Cc by Cb, and where it is B square by 2, so B square, here it is only B square. Now, so this can also be written as Tf plus Ti into Tf minus Ti. So that is equal to minus Cc by Cv B square. And the average temperature can be what there. Let us divide with 2 here. So finally what we get there, Tf minus Ti. So equal to minus Cc by Cv 1 by T average into B square by 2 into B square by 2. So this is what our required equation, change in temperature, that means temperature difference. And here is where T average can be what there, Tf minus T plus Ti by 2, Tf plus Ti by 2, and that is approximately equal to initial temperature Ti. Okay, Ti. So where Tf, so based on this principle, we know that where we can get right side minus, therefore we can say that where Tf is always less than Ti, where Tf is always less than Ti. We know that the temperature, final temperature should be less than the initial temperature. And so in this demagnetization process, the temperature of the paramagnetic substance is decreased. That means here final temperature is less than the initial temperature. And you must remember that here when we'll get maximum cooling effect. When will we get maximum cooling effect? See there, where the intensity of magnetic field is more, when the initial magnetic field density is more, then we can get more cooling effect. And also where higher the Q is constant and lower the specific heat constant, at the time also we'll get more cooling effect. And also when the initial temperature is when the initial temperature is very low, in that case also we'll get more cooling effect. That means initially, before demagnetization, the initial temperature of the substance is very less, that is Ti is very less. So after the demagnetization, we'll get more cooling effect. Okay. So this is all about calculation part of adiabatic demagnetization. It's a very important question. I think you understand well.